Now that you've built your first circuit and learned how to use a multimeter and know what schematic diagrams look like, let's pull back the curtain a little bit. Today, we're diving into one of the most important relationships in all of electronics, the connection between voltage, current, and resistance. And to understand it, we need one of the most powerful tools in circuit analysis, Ohm's law. Ohm's law is the foundation of circuit analysis. Ohm's law links the three core elements of every circuit, and the equation is super simple. It's V equals IR, where V is equal to voltage measured in volts, I is the current measured in amps, and R is the resistance measured in ohms. We can rearrange it as needed, so if you need to find the current and you know the voltage and resistance, you can just use I equals V divided by R. So if you need to find resistance and you know the voltage and current, you can just use R equals V divided by I. The key idea is voltage is the push, current is the flow, and resistance is the opposition to that flow. Let's understand what these units actually mean. Voltage is energy per charge, or joules per coulomb. Current is the flow rate of charge, and that's coulombs per second. And resistance is how much the component resists current. What is a coulomb? It's the unit of charge. It just states the quantity of electrons. It groups a quantity of electrons to a single unit. I like to think of a coulomb as a bucket of electrons. And we're going to be using this bucket to actually represent what it means. Okay, so like we said earlier, a coulomb is like a bucket of electrons. 1 coulomb is about 6.24 times 10 to the 18 electrons. That's 6 followed by 18 zeros, tons of tiny charges. That's like squeezing a bunch of little droplets into this bucket. All right, and voltage is the energy per bucket. A 1 volt battery gives each coulomb 1 joule. A 9 volt battery gives each coulomb 9 joules. So we say that each bucket has that much energy that it can use. Current is the number of buckets flowing through pipes or through the wires per second. And the more current, the more energy is flowing. And resistance is like the thickness of a pipe. The wider it is, the more can flow through. Now, on to the basic rules of electric circuits. We start with the first law of thermodynamics, which says energy in equals energy out. In a closed loop, the voltage supplied by the battery is exactly equal to the total voltage drops across all the components in that loop. We call this Kirchhoff's voltage law, or the loop rule for short. In other words, the battery pushes energy in and the components use it all up, giving us the equation Vin equals V1 plus V2 plus V3 and so on, with the voltage drops across each resistor given by Ohm's law. So, if the battery gives 6 volts, the resistors and other components must eat up that 6 volts altogether. No more, no less. This balance is the key to solving circuit problems. Voltage in equals voltage out. Okay, now let's apply Ohm's law. Let's say we have a 6 volt battery and a 500 ohm resistor. Well, if we wanted to find out the current, we would just do I equals V divided by R. And that tells us that we have 12 milliamps flowing through the circuit. What happens if we double the voltage? Try using a 12 volt battery instead. Now we have I equals 12 divided by 500. And that gives us 24 milliamps. The key here is the more voltage, the more current, assuming the resistance stays the same. Okay, let's try reversing the question. Let's solve for voltage. Let's say we know the current is 0.02 amps and we have a resistance of 100 ohms. Well, using Ohm's law, we know V equals IR. We multiply everything together and we know that the voltage is 2 volts. Ohm's law works in any direction, depending on what values you know. Now, let's talk about what happens when you combine multiple resistors next to each other. We call this in series. Say you have 2 resistors, one after the other. Let's say we have a resistor R1 that is 600 ohms and R2 which is 900 ohms. The total resistance, labeled as R total, is equal to the sum of the resistance value of each resistor. So R total is equal to R1 plus R2, meaning total resistance is 1500 ohms. With a 6-volt battery, we have I equals V divided by R, telling us the current is 4 milliamps or 0.004 amps. So in series, current is the same through all components. So voltage is split across each resistor or all of the resistors. Now, resistors in parallel is like having a fork in the road. You have two directions that you can travel. You have two paths electricity can flow in. So let's try this. Let's say we have a resistor R1 that is 600 ohms and R2 which is 900 ohms. To find the total resistance, you use the following equation. It looks a bit funny, I know, but trust me, it works. You basically plug in all of the resistance values and multiply by a common factor so that we have a common denominator. We then sum the numerators, and once we have this, we flip the denominator and numerator and divide, and that tells us what our resistance value is. In this example, the numerator is 5 and the denominator is 1800. So if we flip those, we get a total value of 360 ohms. So if we were solving for current with a 6-volt battery, we have I equals V divided by R. And so that tells us that we have 16 milliamps running through the circuit. Some key points in parallel circuits: voltage is the same across all branches or paths. Current splits depending on the resistance, so each path can have different currents, and the total resistance is less than the smallest resistor. Last important thing, batteries in series versus parallel. When you have batteries in series, you connect the positive terminal of one to the negative terminal of the other battery, and this results in the voltages adding up, but the current stays the same of what they can dish out. So we can say that the total voltage is the sum of the batteries. So the V total, or total voltage, is equal to V1 plus V2 plus V3 and so forth. Let's look at an example. Let's say you have 4 AA batteries in series with one another. This is the exact same setup in your battery pack. A AA battery has 1.5 volts. And so when you put them all in series, you get a total of 6 volts. This setup is typically used in flashlights, laptops, and RC cars. Cool, but what about batteries in parallel? Well, to do this, all the positives are connected together. The voltage stays the same, but the current capacity adds up. This means that you can dish out more current, or total maximum current, from this combination. Let's look at a quick example. Say you have 3 AA batteries with a 1000 milliamp hour capacity. The output voltage across the resistor is 1.5 volts, and the capacity adds up to 3000 milliamp hours. This means that the overall voltage doesn't increase, but the capacity does, meaning we can run the circuit for much longer. So for batteries, if you need a higher voltage, make sure to use them in series. And if you need longer battery life, make sure you have them in parallel. Need both? Combine both types. This is typically the combination used in electric vehicles, such as electric scooters, electric cars, and so many other things. We made you a summary sheet so you can easily remember all of this. Here are our final takeaways from today. Ohm's law is your very best friend. V equals IR. Remember, voltage is the push, current is the flow, resistance is the opposition. In series, resistance adds and current stays constant. In parallel, resistance decreases and current splits. Coming up next, you'll practice applying Ohm's law to real-world problems. We'll calculate voltage drops, current paths, and power usage, all step by step. Let's sharpen your circuit intuition together, and see you in the next one. If you like what you've seen so far, you should visit our website and check out our electronics and coding kit. It comes with all the videos, all the lessons, all the code, all the labs, and all the project files. So yeah, link in the description, and happy learning.